Good afternoon, ladies and gentlemen.
Good afternoon.
Are there any questions about what we did yesterday? So we did section 9.1 up to 9.3, and we looked at ordinary differential equations, and we tried to construct these functions. Yeah. And what we did so far was constructing Green's functions for which actually the eigenvalue for a nearby problem was not equal to 0. So the eigenexpansion, there was not an eigenvalue corresponding to 0. Today we are going to look where we have such a problem. And that's section 9.4, if there are no questions. And also, if I give a lecture, those of you that have had me earlier in our workshops, if something is not clear, please pose a question. Yeah? Because I hope if you leave this room, then what we did should be clear. Yeah? So, pose questions. Yeah? Also during the lecture. Okay. What did we do? Well, the goal of today is that we are going to look at section 9.4 and 9.5. And in section 9.4, we are going to look at constructing Green's functions for which there is an eigenvalue of the eigenfunction expansion which is equal to 0. Yeah. What is actually what we're doing? We're doing still the same. Lu is some kind of function f of x. Yeah, so we have a linear differential equation with the function f(x). We have some boundary conditions, and we try to solve this problem. And what we try to find is a representation in the form ux is some kind of integral over the interval that we are having. That can be an interval from 0 to L or A to B. And then we have here a Green's function. And then we have a representation for our solution, assuming that we have here homogeneous boundary conditions. Yeah, if we have non-homogeneous boundary conditions, we can use Green's formula and then we get more terms here. Yeah? But then also there we have the Green's function. So that is our goal. And one of the ways to look at it was to say, okay, let's have a look at the nearby problem, the eigenvalue problem, which is equal to this, plus homogeneous boundary conditions. Here we have always homogeneous boundary conditions. That gives us all kinds of eigenfunctions and eigenvalues, lambda n, phi n. And to solve this problem, you might say, okay, I'm going to look for a representation also in the form a sum an times phi n x, where phi n x are the eigenfunctions that we found here. So these are depending on x, and this is just a constant. Then we substitute that into our problem. Lu is f. Substitute that into your problem. Then you have to compute L sum an phi n is equal to f. Interchange summation and differential operator to obtain this. Yeah. Then we know that this is equal to, according to that, minus lambda n phi n. So we will get minus the sum of an lambda n phi n is f. And now we have to determine the unknown coefficients, because this is an eigenfunction expansion. We have to determine an. And to do that, we know that our eigenfunctions, also given here, are orthogonal. So we multiply this equation with phi n, and then integrate over the interval that we are having, whatever that interval is. Using orthogonality, orthogonality phi n functions. And then you find simply that minus am lambda m times the integral from 0 to L phi n squared dx is equal to the integral from 0 to L f times phi n dx, or that gives you the following expression: minus am lambda m is equal to the inner product of f with phi n divided by phi n itself. I also wrote this down yesterday, and if you're going to look what I'm going to do the coming lectures, also for PDEs, you will find similar expressions. Yeah? So what I'm going to do is I'm going to do it in higher dimensions later on, but then the expressions will remain the same. Yeah? I did not specify much here. I did not tell you what this operator is, but it can also be a partial differential operator. Then I still have eigenfunctions and eigenvalues. Then I can still make here an eigenfunction expansion, perhaps in more variables, but that doesn't matter. I substitute it into the differential equation. I will get always this. Then I get always this. I can do this. Yeah? But then this integration will be not over an interval, but might be over a volume. Yeah? So that's a higher order integral, but it remains the same. And then the result will always be this. Because this is an inner product, and that can also be an inner product later on, not only over an interval, but also over a volume. Yeah? So this can be generalized. And that's what you always should try to see if you're studying PDEs. From ODEs to PDEs, you generalize. Yeah, you make it more difficult. Yeah, but the mathematical structure behind this is what's written down here. Yeah, and that's what you, as a applied mathematician, always should see. What's the structure behind my problem? And then you understand that a lot of problems that we are doing, they are almost the same. Yeah, as soon as you become a teacher, and you are going to teach courses in mathematics, you will see, yeah, the whole time I'm actually doing the same thing. Yeah, but from the abstract point of, that's at least from the abstract point of view. Yeah, for a student, okay, this is an ODE, this is already difficult. A PDE, that's even more difficult, but it's the same structure, and that's something you should try to see. Okay, so that's what we found. And now, we can say the following. If all lambda m are not equal to 0, then we find am is equal to minus f phi n divided by lambda m phi n, and u is unique. Yeah, we have a unique solution. If there exists an m for which lambda m is equal to 0, then we have a problem, because then on this side we have 0. We cannot determine am, and that means that also this has to be 0. And if this is not 0, then there is no solution, because then we have 0 is something which is not equal to 0, is impossible, no solution. And if this is 0, then we don't determine am, so there are infinitely many possibilities for am, and then we have a non-unique solution. We have infinitely many solutions. Yeah, so the second statement will be if there exists an m for which that's 0, then there are infinitely many solutions when f phi m is 0, else none. And that's what we call the Fredholm alternative. And that Fredholm alternative is coming back over and over again. This is what we did yesterday. And we constructed some Green's functions. And now I'm going to give you a problem for which the eigenfunctions are existing and we have an eigenvalue 0. So let's consider the case L is a second order derivative with respect to x. Yeah, that's the differential operator, and I'm considering L phi is equal to minus lambda phi, and I define phi prime 0 is equal to phi prime, let's say pi is equal to 0. Yeah, I'm going to look at this eigenvalue problem. I can construct the eigenfunctions. Well, I did it yesterday where I had phi 0 and phi pi is equal to 0, and now I take the derivatives equal to 0. If you're going to solve this, then it will turn out that you will get cosines. Yeah, because you have to solve here the equation phi double prime plus lambda phi is equal to 0. That's equivalent by saying, well, I'm getting cosines and sines as solution. And phi prime needs to be 0, and that means that you get cosines back. Yeah, you all understand that? Do I have to write it down? Write it down? Yep. Okay, so you get phi x is c1, and I know that lambda is positive. Cosine square root lambda x plus c2 sine square root lambda x. Then apply the conditions. Phi prime 0 is equal to 0. That implies that c1 times the sine square root lambda times 0 minus sine plus c2 square root of lambda times cosine square root of lambda times 0 is 0. That implies, what does it imply? C2 is 0. And this formula is only valid for lambda positive. Yeah? This formula is only valid for lambda positive. If lambda is 0, I should also write down phi x is c1x plus c2. And this formula is valid for lambda is equal to 0. Okay, so complete. So if I go up, then I will see that if I take phi prime 0 is 0, then that implies that c1 is 0. Yep. Then I have the other condition, phi prime pi is equal to 0. Well, c2 is already 0, so that means that minus c1 square root of lambda sine pi, what is it, square root of lambda, sorry. Should be equal to 0. And that implies that the square root of lambda is equal to n, and that n should be an element in z plus. Yeah. Do the same thing here. Phi prime pi is equal to 0. Differentiation gives me again c1 is 0. So here I will find, if I go up, that my phi x is c2. And that's actually equal c2 times 1. So 1 is an eigenfunction belonging to the eigenvalue 0. Yeah? So this is belonging to each other, and this is belonging to each other. Yep. And here we have lambda is n squared, are eigenvalues. With eigenfunctions phi nx is equal to cosine nx. Okay. But the interesting thing is that we have an eigenvalue lambda is equal to 0. In between brackets, I'm going to study this problem. I would like to study that problem. The Green's function has to satisfy the same differential equation but in the right hand side the delta function, where in this case x0 is in between somewhere 0 and pi. Yeah. And I have as conditions dg dx at 0 is equal to dg dx at pi, and that's equal to 0. So I have to solve this problem. Lambda is 0 is an eigenvalue. Dus if I apply the eigenfunction expansion, lambda 0 is eigenvalue, then I have two possibilities, no solution or infinitely many. So if I try to construct the Green's function, I have only two possibilities, no solution or infinitely many. And I have to look at the inner product, fx, inner product with the function for which lambda is 0 is an eigenvalue. So I have to look at the inner product that I'm writing down here. So I have to look at the inner product, in this case, the delta function, x minus x0, comma 1. I have to look at that inner product. You agree? Because f is the delta function. And for which function do I have an eigenvalue lambda 0? That is the function 1. So I have to look at that inner product. So I have to compute this, the integral from 0 to pi, delta x minus x0 times 1 dx. What is the outcome? 1. That's not 0. You agree? Not 0. So this problem, no solution. So what I did earlier, when there were in fact no eigenvalue 0, yeah, then I could solve this, and then I could work with it, and then I could use Green's formula, and I have a nice solution. It doesn't seem to work. Remember that I'm only interested in one function g. Yeah, I only would like to have one function g because then I use Green's formula, and if I found one solution, then I will find all solutions. Yeah, whatever the Green's function is. Yeah? Okay, keep that in mind. Go back to this problem. Go back to this problem. I know that an eigenvalue lambda is 0. So I also know that this problem is only solvable, there is a solution, if that inner product is 0. Or equivalently, when the integral from 0 to pi fx times 1 dx is equal to 0. So I can only solve this problem if I have an additional condition on f. That integral over f should be 0. So that's a mathematical statement. Yeah, this problem is only solvable when that integral over f is 0. And if I look at this problem, it's not solvable. Yeah? Okay. Now going back to physics, so that's still in between brackets. Consider this heat equation. And let's consider the boundary conditions. Ux0t is ux pi t is equal to 0, and take as an initial condition, well, not f, let's take a g over here. Consider this problem. Yesterday I considered this problem, but only with Dirichlet conditions. Here I have Neumann conditions. What does it mean physically? Well, I have a rod, and the temperature is given by U. And what does it say? My PDE tells me that the heat transfer, okay, is this, diffusion here, production term here. So somewhere here I have something where heat is produced. Yeah, so inside the rod I have production Q. Yeah, think of a rod in which you have an electric wire, and then through that electric wire there is some current, yeah, that produces heat. That's Q, my equation. What does it tell me? This boundary condition means that the heat flow to the boundary is 0. So what I do is this end is insulated, and this end is also insulated. And if you derive this equation, then you also assume that the outside is insulated. So you have a completely insulated rod. You have a completely insulated rod. That's this physical model. Okay. Now I'm going to look at a time-independent solution. I'm going to look at a stationary solution, time-independent solution of this problem. Time-independent solution is described by the following equation. There's no time dependence, so the u derivative is not there. And I will get that k times uxx is plus qx is equal to 0, or equivalently uxx is equal to minus qx over k. Yeah? Time independent solution, there's no time dependence, so I will get ux at 0 and ux at pi is also equal to 0. So it's described by ux0 is ux at pi is equal to 0. Yeah? Okay. Hey, let's have a look. Uxx is equal to a function of x. Uxx is a function of x. Hey, that's the same problem. U prime at the boundary is 0. U prime at the boundary is 0. So this problem corresponds to the stationary solution of a heat transfer problem for which the outside is completely insulated. No heat can go through the boundary. Yeah, so no heat can go through the boundary. Yeah, so the heat that's inside cannot go out, and there can no heat come in from outside. Okay. I'm looking here for a time-independent solution. So I'm looking here for the stationary solution. If there is a stationary solution, what is then the condition on the heat production inside? Yeah? In this room, let's have a look at this room. There is heat production. You all are producing heat. Heat is taken away over there. And heat, yeah. And what do we have here? We have a stationary solution. The temperature is around 24 degrees. Yeah? Stationary solution. Heat produced, heat taken away. When do we have a stationary solution? If the total heat that is produced in this room is equal to 0. Yeah, you agree? Yeah. Total heat production is 0. You produce, that's taken away. Total heat production is 0. So the sum over what I have here as production should be 0. If I call this F, then the sum over F should be 0. That means that the integral over F should be 0. Hey, the integral over F should be 0. It's the same. I only have a stationary solution if the heat production is equal to 0. Here I had a mathematical argument to say that this integral needs to be 0. Here I give you a physical argument that that integral has to be 0. And you see how nicely it fits. Yeah, you agree? Okay. So the problem here is only solvable if the heat production is 0. Here I have a non-zero heat production. The problem is not solvable because it's a stationary problem. Okay, but now I have to think further. So here I can end my in between brackets. What do you do if you have as a problem, as a mathematician, a problem that you cannot solve? Approximate it. Usually what you do is you take another problem, which you can solve. Yeah? Yeah, so you forget about the non-solvable problem. Or make this problem solvable. Yeah, and that's what we are going to do. So we're going to make this problem solvable. And that's what we're doing in section 9.4, and we call that not Green's functions, but we call that generalized Green's functions. Yeah? Generalized Green functions. So what we would like to have is a problem like that. And I would like to have it solvable. What they do is the following. They usually do it in the following way. You can do it in infinitely many ways to make a problem solvable. So what they do is they multiply it here with a constant c times the solution for which I have an eigenvalue 0. Yeah. Constant is still not known, but the constant will be determined such that the problem becomes solvable. And I would like to have a solvable problem. So I should determine that C in such a way that the problem becomes solvable, and that means that the integral from 0 to pi in this case of delta x minus x0 plus c times phi lambda 0 x times that function dx, and that is 0. Because if it's 0, then it's solvable. Yeah, you agree? Yeah. So I will determine c. Now I know in this case that this function is 1 in the example, and also here it's 1. So I have to compute the integral from 0 to pi delta x minus x0 plus c times 1 dx. And I have to compute in such a way that this is equal to 0. Well, the integral from the delta function times 1 integrated over that interval just gives me 1. And that's 1 plus c times pi. That should be 0, and that implies that I should take c equal to minus 1 over pi. Then I have a solvable problem. Okay, then that means that I should now solve the following problem. I should solve this problem. Yeah, with conditions, dg dx at 0 is dg dx at pi dx is equal to 0. I have to solve this problem. Determine g. So if I can determine g, then I can solve also the original problem because I have Green's formula. Yeah. Okay. How do we solve this problem? So now for this problem I would like to determine g. How do we do it? Same as yesterday. Yeah. Mathematics is not so difficult. You do a lot of things over and over again. Yeah. So solve it in the same way. So let's assume that x is smaller than x0. Then I have to solve the equation. The second order derivative is equal to minus 1 over pi. Integrate it once. Then you will get dg dx is equal to minus 1 over pi times x plus a constant c1. I know that dg dx at 0 is 0, so c1 should be 0. Yeah? Yeah, and I'm working for x smaller than x0, so I should use this boundary condition. So I will find that this is equal to minus x over pi. Then I integrate it again, and I will find that gx is equal to minus x squared over 2 pi plus a constant c2. Okay. Then for x larger than x0, do the same thing. Integrate it once, like this. And then we say, well, dg dx at pi is equal to 0. So that means that my c3 is equal to 1 over pi. Equal to minus 1. Sorry, to 1. Yeah, so if I dg dx at pi is equal to 0, so if I substitute pi, then I should get 0, so c3 should be 1. Yep. So I get minus 1 over pi times x plus 1. And that also gives me then that gx is equal to minus x squared over 2 pi plus x plus c4. Now I have two conditions. I also have two still arbitrary constants, c2 and c4. One condition was that the function g should be continuous. Well, on the interval up to x0 it's obviously continuous, and from x0 on it's also continuous. So I only should make it continuous at the point x is x0. That's one condition. Yeah, so that's I'm going to write down in a moment. The other condition is that there should be a jump in my derivative. So if I integrate this equation from x0 minus to x0 plus, then this gives me dg dx just after x is x0 minus x is the value of dg dx before x is x0 is equal to 1. And this integral from x0 minus to x0 plus gives me 0. So the jump in the derivative should be 1. Well, let's have a look. dg dx minus x over pi plus 1. I have already satisfied the condition that there is a jump in my derivative. Yeah, you agree?
Yeah.
You see, plus 1 difference. So that's automatically satisfied. So that means also that I will get only one condition and two free variables, xc2 and c4. So I will never determine my g uniquely. You agree? Do we expect that? Are we expecting that the solution of this problem is unique?
No.
Why not? We have an eigenvalue 0, we make it solvable, and how many solutions do we have? Infinitely many. Ah, that agrees with that. So you see how nicely all things fit. Yeah? Okay. Let's write it down. Yeah, so we already satisfied the second condition. Well, let's go and continue with making it continuous. So we'll find this. Okay. Gx is equal to, well, let's write it down. Minus x squared over 2 pi plus c2 plus x0 plus c4, and that's for x smaller than x0, and it's equal to minus x squared over 2 pi plus x plus c4, and that's for x larger than x0. Yeah? You all agree? You agree so far? Yes? Okay. We also know that if lambda is 0 is not an eigenvalue, then we have also that nice property that the Green's function is symmetric. So if we interchange x and x0, we will get the same formula. Well, here we still have some freedom. The question is, can we make also this Green's function symmetric? Yeah, so this is the correct answer already, so don't worry about it. Yeah, but can we make it by a special choice? Yeah, because we have infinitely many solutions here, because C4 is an arbitrary constant. Yeah, can we make it nicer? And that's also what a lot of mathematicians do, they make this also symmetric. The question is, can we make it symmetric? Yeah, so we're trying to do that. Okay, well, let's write down the formula. And what we also can see here in this formula, and I will write it down in blue. C2 is depending on x0. Yeah? It also means that, of course, if you rewrite it, that C4 depends on x0. So I can also indicate here the dependence on x0. Yeah? Due to this relationship. I can do that if I wish. Yeah? So you can imagine that there is here an x0 dependence in this formula. Yeah? Due to this formula. If I write down the formula for x smaller than x0, so that means if I write down x0, x, then the first argument is larger than the second argument. If I look at this function. Yeah, so the first argument is larger than the second argument. So I should use this formula, the lower one. But then with x0 and x interchanged. Yeah? So look, let's do that. So on this side then I will have minus x0 squared over 2 pi plus x0 plus c4x. Yeah? Is equal to gx x0, first argument less than the second argument, so I should take this part. So I will get minus x squared over 2 pi plus x0 plus c4 x0. What do I see? Pleasantly, x0 here and x0 there cancels. But then how to continue? So I can make it a little bit more simple. Put all the x0s on one side. Minus x0 squared over 2 pi plus minus c4. Is equal to minus x squared over 2 pi plus, minus c4x. Yeah, then I get this expression. What does that tell me about c4x? I would like to know what is c4x in my formula, because I want to determine c4. This is the condition that leads to a symmetric one. Yeah? This is a symmetry. And then I have to satisfy this. What do I now obtain? It has nothing to do with differential equations. It has nothing to do with differential equations. What can you tell me? What should C4 be? C4x should be minus x squared over 2 pi. Is that the correct answer? It is an answer. It satisfies. Yeah, so you'll find the Green's function. But if I take C4 equal to x squared over minus x squared over 2 pi, then I will get a unique G. You agree? And I know that the solution is non-unique. To each Greek function, actually if you look at your problem, you have the second order derivative is the delta function plus, it was minus 1 over pi, it was? 1 over pi, yes, okay. And then the gdx at 0 is equal to the gdx at pi is equal to 0. So to each solution, I can add a constant. And a constant in each solution is just symmetric. Eh? But it does not destroy the symmetry. I'm missing that constant. separation of variables. At least most of you did the method of separation of variables. There you separated time and space. On one side we have x, on the other side t. On this side I have x0, a function depending on x0, and here I have a function depending on x. They are independent. When are two functions equal to each other? If there are independent variables, if they are equal to a constant. So the solution is minus x squared over 2 pi plus, minus c4x should be constant. Yeah, so then I see that my c4x is equal to minus beta plus x squared over 2 pi. Minus wrong again. No. Yeah, minus. Yeah? So this is my C4. Okay, so I can substitute that into my formula. And here I nicely have my green function. Of course, we are usually only interested in one, so we take beta equal to 0. Yeah? And then we use Green's formula. And what was Green's formula? Well, that was the formula, the integral in this case from 0 to pi, because that's the length of my interval. I had ulg minus glu dx, and that's equal to, in this case, the integral from, the boundary of u dg dx minus g du dx on the boundary from x0 to L. Yeah, that's the formula of Green. And now I can just substitute into this problem my g, it's up there, and I can substitute what I know about my u, because Lu is in this case f, x, Lg in this case is equal to delta x minus x0 minus 1 over pi. Yeah? And this gives me the g dx is always 0. And in this example, the u dx is also 0 on the boundary. Yeah, but if you take their values alpha or beta or whatever constant you take, yeah, but here now, yeah, it's in this case 0. Yeah? So I will get as a solution u x0, that's u times the delta function. Yeah, you agree? Then I have u times 1 over pi integrated over that interval. Minus 1 over pi integral from 0 to pi u x dx. Yeah, that's what I get. Then the next thing, minus the integral from 0 to pi g x x0 fx dx. Okay? Is equal to, well, if I take this 0, then I have all zeros over there. Okay. So the solution at point x0 is this integral. Okay, that looks much like what I received earlier. But now I have this. What can I say about this? The integral over the complete interval of u. That will give me a constant, eh? You agree? This integral will always give me a constant. But the question is, what's the constant value that I get over here? Is it 0? I sum the temperature. Okay, let's think again in this room. We have a stationary solution. We are constructing a stationary solution. Yeah, so the problem that I'm solving here is that stationary temperature problem in this room. You're producing heat, heat is going out of there, net heat production is 0. What do I sum over here? The temperature. And I divide it by pi. So what I'm computing here? The average temperature. Okay. So this is the average temperature. What can I say about the average temperature? Yeah, of course it's a constant. Yeah. In a stationary solution, but what is here now the average temperature? 24 degrees. Yeah. If I go back to my original problem, I said, well, think of a heat equation. K uxx plus q x, and my fx in that formula, over there in the formula, that was equal to minus qx over k. I had my boundary conditions, so ux 0t is ux pi t is 0, and I had my initial temperature. So here it can be warmer than over there in the corner. And I have to have here the initial temperature. So what can I say now? How is this integral related to this problem? How do I get from this problem my average temperature here? What should you do? Well, I have here an integral from 0 to pi. Yeah, so be very lazy and then say, okay, I would like to have an integral from 0 to pi. Let's integrate the PDE from 0 to pi with respect to x. Yeah, so do that. So this is our problem. Then you get the integral from 0 to pi ut dx is equal to the integral from 0 to pi k times uxx plus qx dx. Okay. Here I integrate with respect to time. Sorry, with respect to x. This is differentiation with respect to time, so I can take out the time derivative. So I look at that the time derivative of the integral from 0 to pi uxt dx is equal to, hey, that's pleasant, I have here an integral over 0 pi dx. Oh, that looks already a little bit like this. The integral from 0 to pi u dx. Pleasant. Okay, but I have here the time derivative. Okay, nasty. Let's continue. I have to integrate this term, k times uxx. I can immediately integrate that. That gives me k ux in between x is 0 and L. Yeah? And then I have plus the integral from 0 to pi qx dx. What do I know if I substitute the upper bound? 0. What do I know if I substitute the lower bound? 0. Because I have these boundary conditions. There is no heat flow. So this is 0. What do I know about this integral? That was the net heat production. You're producing heat, heat is going out over there. That integral is 0. Yeah? So this is 0, this integral. Okay, so the time derivative of this integral is 0. The ddt of this integral of uxt dx is 0. So that means that this integral for an arbitrary time is constant. And to what is it constant? To what we have at t is equal to 0. Eh? So this is for sure equal to the integral from 0 to pi ux 0 dx. What is ux 0? G. Gx, that's my initial temperature. Here it's warmer, there it's cooler. Yeah, that's my Gx. Okay, so what do I know? This temperature, this integral, is always constant. To what is it constant? 1 over pi, integral from 0 to pi, gx dx. That's the average initial temperature. So you see that the solution in an arbitrary point at a certain position is equal to the average temperature plus the integral g times f. And now I have my complete solution. And now you see one thing that's very important for people that are working only in pure mathematics. It's hard to solve this problem if you're only working in pure mathematics. Because at a certain moment I used physics. Yeah, to help me solve the problem, to determine what does it mean, heat flow, initial temperature, heat going in, heat going out, and it helps solving you the problem. It gives you the way how to tackle the problem mathematically. And that is typically what applied mathematicians are doing. So applied mathematicians, they know something of applications, they know something about pure mathematics, and then you have the combination and then you can solve a lot of problems. I do this by heart. Yeah? But that's because I'm teaching a similar course in my institute and I do it so many times that I know it by heart. Yeah, but I always have to think, what step do I have to make? Yeah, and then also, I always think of the physics and that helps me immediately in solving the problem mathematically. Okay, it's good now to have a 10-minute break, and after the 10-minute break we are continuing with problems in Rn. Yeah? So after the 10-minute break, because we now have almost 1 hour lecture and it's not easy this, so I give you a break of 10 minutes and after 10 minutes we continue again with a little bit of theory. Yeah? And at the end I have 2 exercises for you, one that you can do and I will give you an extremely difficult one. Yeah? An extremely difficult one, Aditya. I'm challenging you. Okay, 10-minute break. I wash my hands. Now we are going to PDEs. Yeah, so now we really are going to generate and extend the concept of Green's functions to Poisson equation. What is a Poisson equation? That is the Laplace equation is equal to f in a certain domain, and you have boundary conditions on the boundary of D. Yeah, and the boundary of D, there might be no boundary, then it's infinite. Yeah, so essentially we are looking at an equation. If you look in R2, then you're looking at the equation uxx plus uyy is equal to the function f of x and y. Yeah, and you might, for instance, have u is 0 on the boundary. Yeah, so you might have a domain like this, then this is your D, and then this is your boundary. And you might have that situation. Yeah, so you might look, for instance, at this problem. And what we always have on such a boundary, we have an outward normal vector. Yeah. Okay, but it might also be a problem that your D is just the whole domain, yeah, the whole space. No boundary. Yeah, that might be also D. And in physics, you usually assume that there is no energy at infinity, and that means that u and all of its derivatives are 0 at infinity. Yeah, that's your assumption there. But here you might specify, for instance, on this boundary that your temperature is 0. What does this problem mean physically? Well, it looks like the heat equation, but then you have one dimension more. So you're describing the heat, the temperature in this plate, for instance. Yeah, and you specify the temperature on the boundary to be 0. That might be also that you say there is no heat flow through the boundary. Yeah, so you may subdivide this boundary in more than one boundary, and then your D might also be something like this. That this is your boundary D1 up to here. Then you have here a boundary D2 up to here, and here you have a boundary D3. Yeah, so that means then that your boundary of D, if this is D, is the union of all the boundaries. Yeah? And then here you might specify, for instance, u is a function f. Here you might, for instance, specify that the udn is 0. That means that there is no heat flow through that boundary at that point, at that interval. And here you might say, for instance, that the heat flow, the udn, is proportional to the temperature. Here you have a Dirichlet condition, here a Neumann condition, and here you have the Robin condition. Yeah? Heat flow is proportional to temperature. Here you prescribe the temperature, here there is no heat flow. Yeah? That mixture you can have. Yeah, those are typical boundary conditions. So that's what if I write down here, I have the Laplace of f in a domain, and I have boundary conditions on the boundary of my problem. And in R2 you can think of such problems. You can also have something in R3. What are you looking at? There is no time involved, so you always look now at this moment at stationary solutions. And it can be the stationary solution of a heat problem, but it can also be the stationary problem for a wave equation. If it's two-dimensional, then you have a membrane. So you look at the stationary solutions of a membrane. Yeah? And for instance, imagine that you have a membrane, and you prescribe on certain boundaries its displacement. I hold it fixed here, for instance. And then the membrane on the other end is free. Then I take this membrane, for instance. I keep it like this, and then you see free ends over here, and here I keep it fixed because I have my hands there. And then I wonder, how is this membrane? What's the shape of the membrane? And if I do this, what is the shape of the membrane? And so here I prescribe U is, well, let's say almost 2 meters. Here it's 1.7. So how's the membrane hanging? Yeah, and that's a stationary solution, and that's the problem that you try to solve. Yeah? Okay, to solve this problem we are going to use Green's functions again. But Before we go to the Green's functions, and the Green's functions will be quite simple, we have to solve the problem. Laplace g is delta x minus x0. Yeah, so on the right hand side again a delta function, and homogeneous, the same type of boundary conditions, but homogeneous boundary conditions for g on the boundary. So we have to solve this problem. So that's almost the same as the ODEs. So we're doing this exactly the same thing. But I would like to have a Green's formula. So I have to derive the Green's formula in higher dimensions. And that's what we call later on Green's second identity. So the equivalent of Green's formula for n is 1, space dimension 1. For higher dimensions, that's what we call the Green's second identity. And I'm going to derive that. Yeah, it's not so difficult. And I will take the mathematical approach to prove that. Green's first and second identity. Okay. Let u and v be two arbitrary functions. Yeah, quite simple, two arbitrary functions. And with arbitrary we mean they are sufficiently smooth, and if I need a derivative of that function, it satisfies this property. Yeah? Two arbitrary functions sufficiently smooth. Let's consider this quantity. U Vx differentiated with respect to x. What do I get? I will get U Vxx plus Ux Vx. Okay. And I assume that those arbitrary functions depend on 2 or 3 variables. Let's for this moment assume that U is a function depending on x, y, and z. And let's assume that v is a function depending on x, y, and z. Yeah, you can take 2 variables, 3 variables, 10 variables if you wish. Yeah, but I don't have so much blackboard. Yeah, but it goes in the same way. Okay, so if I have here x derivatives, I will also look at y derivatives and z derivatives. So I take u v y differentiated with respect to y, and then I get u v y y plus u y vy, and the same thing I do with v z z, and then I get u times v z z plus u z vz. So that's quite easy to do, isn't it? Now I will add those 3 expressions. I will add these 3 expressions. And now I will use the following. You are all familiar with the Nabla operator. That is this vector, e dx, e dy, e dz. Yeah, the Nabla operator. You're all familiar with that, huh? Yeah. Or the gradient, if you later would like to do that. So I can write this in the following way. If I add those 3 components, the inner product of the Nabla operator with the vector u vx, u vy, u vz. Yeah? That's what I can write down. If I add those 3 components, then I can take out u, and I can write this as u times the Laplace of v. Because the Laplace of v, the Laplace of a function, is just the second order derivative with respect to x, plus the second order with respect to y, plus the second order derivative with respect to z, if I'm working in 3 dimensions. Yeah. And the last, I can add it up, and then if you look careful, then I have actually here the inner product of the Nabla operator acting on U, the inner product with the Nabla operator acting on V. And I can make it even more simple. I can even make it more simple because within this vector here, I can rewrite it as U times the gradient of V. Yeah, so I get a nice expression, inner product of the Nabla operator acting on U gradient V is equal to U times the Laplace of V plus the inner product of the Nabla operator acting on U, inner product with V. Okay, and I call that formula star. So I have two arbitrary functions, sufficiently many times differentiable, and I get this expression. I can do it also in another way. I can interchange U and V. Then it's also still true. Yeah, so I can also write this as the inner product of V gradient U should be equal to V Laplace of U plus, yeah, that's the same if I interchange U and V. Then what I will be doing is the following. If I have those two expressions, I will subtract the two expressions from each other. Minus. What do I get over here? I get the gradient, inner product, U gradient V minus V gradient U is equal to U Laplace V minus V Laplace U. And this cancels. Okay. And this is what I call formula double star. Formula double star. Okay. Now I should look at my problem. I would like to solve Laplace U is F in a domain, and I have boundary conditions on the boundary. So my differential operator is a Laplace operator. Yeah, you can also write this down in short notation. LU is F. LU is F. Yeah, you agree? Well, if I have here LU, LV minus V, LU, that looks like Green's formula that I did earlier. Yeah, so I have here U, LV minus V, LU. Hey, that's the same. What did I do with that in that situation? I integrated that over the interval. So what I'm going to do is, I'm going to integrate this over my domain, and I'm going to integrate this over my domain. Yeah? This will lead then, later on, to Green's first identity. This will lead to Green's second identity. And we see what happens. Integrate star over D. What do I get? I get the integral. There are my notes, so I don't worry about that. The integral over D of first, then I get I just integrate over my domain, nothing else. But now, if I look to the left-hand side, I see here the divergence of a vector field. This is the divergence of a vector field. Do you know a theorem? When you have the divergence of a vector field and you want to integrate it over a domain? Which theorem do you know about an integral? The divergence theorem of Gauss. Yes? The divergence theorem of Gauss. Then this integral becomes an integral over the boundary of my domain of u gradient v in a product with the outward normal vector. And this is the outward normal vector. Outward normal vector on V. And that's equal to that expression that I have over here. And that's what we call the first identity of green. I'll come to that integral later. There are some nice properties. Next, integrate double star over E. Do the same thing. So we get the integral over my domain D I have this expression. Here again I can use the divergence theorem of Gauss. And then I get the integral over my boundary u and for this inner product we sometimes also write dvdn, the directional derivative of v in the direction n. That's a short notation for this. Yeah, so then what you usually get is this u dvdn minus v dudn ds is equal to the integral over my domain of u Laplace v minus v Laplace u dv. And that's what we call the second identity of green. Is it difficult to derive? The answer is no. You only have to know the divergence theorem of Gauss. If you look careful, for instance, the last formula, this one, it looks much like the Green's formula, but only in higher dimensions. ULV minus VLU And then we found that we had to substitute upper and lower bound. And here we have to integrate one dimension lower over the surface, but it's still u dv dn, v du dn. In the formula of green it was u dv dx minus v du dx. Yeah, so this is just a few dimensions higher. Yeah, and I proved it now for R3, but if you take more components, it's also valid in Rn. Yeah. So this is actually what we will need. Okay, some nice applications. And there are many more. I give just a few. Yeah, take the first identity. And take in the first identity u is equal to 1. Identity equal to 1. And let's assume that Laplace of v is, let's say, qx, and the vdn is, let's say, gx in the and on the boundary. What does it mean? We have a certain domain D. We have heat production. We have heat production Q. So here we produce heat, Q. What does this mean? That the heat transfer through the boundary is given by the function Gx. So heat is going out or in, and that's given by Gx. Yeah, there might be going in here some Gx, and here there might be going out some. Yeah, that's what it states. Yeah, the heat flow through the boundary is given by G. Okay, let's have a look at the first identity. I wiped it out. Yeah. Can someone tell me what the first identity becomes? If I take u as 1, I look at me in my notes. Yeah, so we get the integral 1 times dv dn. Yeah, over the boundary. ds, at the surface, is equal to the integral over the domain of 1 times Laplace v, and Laplace v is q. Yeah, you can also take that depending on y if you wish. Yeah, so x and y and z even. Let's do it in general. Yeah. So that's your q, dv, plus, and that integral becomes 0, because the gradient is 0. So if I write down this, then dv dn is of course g, and then I get the integral over the boundary, gx ds, should be equal to the integral over the boundary of the domain of q dv. Hey, that's strange. I have a partial differential equation. Laplace v is q. The vdn as boundary condition should be equal to g. I apply the first identity, and the first identity mathematically tells me that the integral over g should be equal to the integral over q. And if it's not true, then I will not have a solution, because this is mathematically true. So I cannot take q and g arbitrary here. Can you give me a physical explanation? Can we understand that? Can we understand, if you look at the physics of that problem, that that condition is reasonable? Yeah, mathematically it's sound, but is it physically reasonable? Okay, so let's have a look at this room. The door there is open, so heat is coming in. No, in this case it's coming in. Here, heat is going out. So that's my G. Heat is coming in through the boundary.
Yeah.
You are here, you're producing heat. So you are Q. We have a stationary solution at the moment. And the temperature is now 24 degrees everywhere. Stationary solution. Hey, the problem describes a stationary solution. You are producing heat, heat is going in or out. Stationary. If it's stationary, what does this tell me? Yeah, this is the total heat through the boundary. The total heat through the boundary should equal the heat that we are producing here. And if that heat is not equal to each other, then we cannot have a stationary solution. And that's mathematically what the formula tells us, but also if we give the interpretation of the physics, then it's completely in agreement with the physics. Is it nice? That's a nice application. Yeah? Okay. And this application for the second identity we are going to use for the Green's function. Because what I'm going to do later, the U is satisfying the problem I would like to solve, and V will be my Green's function. And then I have an expression, here a Green's function, here U. So here I will get something what's happening through the boundary. Here I will get U Laplace V, that's the Laplace of the Green's function. That's a delta function, so here I will get my solution in a certain point. Here I get V Laplace U. Laplace U is Q, that I get the Green's function times Q. So here I get an integral I can in principle compute. This is all known, here I have my solution. And I will use that second identity in the same way as I did in Green's formula for an ODE. Is that clear? Yeah, so later on I will refer to this. Okay. I did not prove that yesterday, but we could see from the Green's functions that they were symmetric. Yeah? So the g of x0 is equal to the g of x0x. I'm now going to prove that for you in dimension n. So I do that in one step. So that includes n as 1. Yeah? And I will use this identity. What do I assume? What do I assume? I have a function u which is equal to the Green's function due to a source, source in the point x1. And v is a Green's function due to a source in the point x2. And now I will apply the second identity. We already know that G, the boundary conditions for G on the boundary will be 0. Yeah, so I always want homogeneous boundary conditions. So what do I get? The integral over the boundary of G x1 times dg dn x2 minus g x2 times dg dn x1 ds, that should be equal to the integral over my domain of g x1 Laplace g x2 minus g x2 x2 Laplace g x x1 dv. Yeah, just substituted u and v in my problem. What do I know? G, or the GDN, is for instance 0 on the boundary. Yeah, I always have homogeneous boundary conditions for my G. So this integral on the boundary will always be 0. Yeah, so this integral will always be 0. That integral is 0. So I will get then that 0 is equal to, well, what do I know? The Laplace of g is equal to the delta of x minus x2. And the Laplace of g in the point x1 is equal to the delta of x minus x1. Okay, now integrate. Let's see what happens. If I multiply gx with this delta function, then I get gx2 x1. Minus, and if I integrate this, the delta jumps in x1, so I get x1 x2. And that should be 0. And now you see nice the symmetry. The g x1 x2 is equal to the g of x2 x1. So the Green's function is symmetric. And I did that now for Rn, so that includes R1. Clear so far? Yeah. Okay, then I have an exercise for you. And the difficult exercise I'm going to give you tomorrow, because I have to derive certain Green's functions. But the exercise that you are able to make is the following. Out of the book, make exercise 9.4.8. That is out of section 9.4 and then the 8th exercise. Yeah, so we now take a break, and after the break you're going to make that exercise. And if you have questions about the exercises I gave you earlier, those two, pose the questions. Yeah? What are we going to do tomorrow? Tomorrow we are going to determine in an infinite dimensional space for the Poisson equation, we are going to derive the Green's function in R2 and in R3. So that's in an infinite space. If we have those functions in an infinite space, it turns out quite easily that we can find Green's functions for half spaces. So let's say in a three-dimensional space, the space above the plane Z0. But also we are going to look at regions where we, for instance, have a quarter plane or a sphere or a circle. So also for those domains we are going to derive the Green's functions. So for a lot of domains we are going to compute the Green's functions. Why are Green's functions important? For several reasons. If your domain is not so nice, you cannot compute it analytically anymore. So if it's not a nice sphere or circle or cube or whatever, then you cannot compute it analytically anymore. Then you have to do it numerically. So if it's roughly shaped, yeah, then you have to do it numerically. But you would like to know whether your numerical method works fine. So you have to know test problems. And those test problems are the problems for which you know the exact solution. And that's the reason why Green's functions are important. There's another thing. If you know the Green's functions for a linear problem, a lot of your problems will be nonlinear, or are perturbations of nonlinear problems, or are perturbations of linear problems. But then you can rewrite your problem in an equivalent integral equation. And if you want to treat a problem numerically, then it's more easy to use an integral representation than a differential form. So it's also convenient to go from one form to another form. Yeah. Moreover, there are a lot of open problems for which it's not known yet, or not known yet how to get in an efficient way your Green's function. For instance, if you have a sphere, yeah, or a circle, yeah, and you have a bounded domain, then you can always say, okay, I'm going to apply separation of variables. Yeah, then you have, for instance, if you take it in the plane, then you can use polar coordinates. Yeah, then you can solve that problem, but your eigenvalues satisfy a transcendental equation, so you don't know exactly what your roots are. Yeah, but you know you can solve the transcendental equation if you wish. Moreover, your solution will be in an infinite series form, yeah, because you get your Fourier series if you apply separation of variables. I will show you tomorrow that also for those domains you can get a more compact form, so you can sum up in one step the whole Fourier series. But then, for other type of boundary conditions, it's not known how to do that. So then you're on immediately in the research field. And one of the extremely difficult exercises is related to such a problem, yeah, for which it's not clear yet how to do it. At least some of us now know how to do it, but we are just testing if you can also find that solution. Yeah. Okay, but then that's the goal of what we're going to do tomorrow. For today, practice exercise 9.4, that's still on ODEs. Yeah, and you can still see if you understand all the things about your ODEs. Yeah. We now have a break, and then after the break, well, we continue with the exercise. Yeah.
Yes, it's fine. 9.4.
gentlemen, in this exercise, 9.4.8, and if you already try to make that exercise, then you will see that in part A, you will find infinitely many solutions. Lambda is 0 is an eigenvalue, but the eigenfunction sine x belonging to lambda is 0 will give you still a solution of the problem, because the inner product fx phi, for which lambda is 0, that inner product is 0, so you will find infinitely many. In the second example, you will find lambda is 0 again as eigenvalue, and then you have eigenfunction sine x and cosine x, but then the inner product f with an eigenfunction is not 0 in all cases. That means that you have no solution. So in the first case, you have infinitely many solutions. In the second case, you have no solution. And then as additional question, you can pose the question for part A, where you have infinitely many solutions. Can you construct also for me the Green's function? Yeah, so that's an additional exercise. Construct the Green's function for 9.4.8a. Yeah, because there are infinitely many solutions. Yeah, and then you will have to construct a generalized Green's function. So you will have LG is delta plus C times phi x for each lambda 0. Then determine that C, and then try to construct a symmetric Green's function. Yeah? Okay. Question? Okay, you're homogeneous, that's lambda 0. Because that's by one of the undefined sides. So lambda 0 is the eigenvalue with eigenfunction sine x. Then you compute the integral. Yeah, then I yeah, you have this. And then you have to compute. Yeah, okay, wait for one. The first important question, is this problem having a solution? So then, yeah, or not? I don't know. Lambda 0 is an eigenvalue. You said no. So it cannot be unique. Yeah? Infinite or no? That's the possibility. So you have to compute fx times eigenfunction for which lambda is 0. That turns out to be 0 in this example. But in the next part of the exercise, 9.4.8b, I don't know what it is. Yeah, for in this case, then it turns out, yeah, you can see already here. It will construct here the general solution.
Yes.
Yeah? So this you can see that we never get satisfied with the lower bound. Yeah? But you can also see it from another point of view, because we saw that we had to look at f h in a product with phi homogeneous x. Is 0 question mark? No. And that means that? Yeah, no. First year, when you did your bachelor, you try to solve that. Second year, okay, second year. And then you solved it, and then you knew that if the determinant of the matrix is non-zero, then this problem has a unique solution. If the determinant is equal to 0, then there were two possibilities: no solution or infinitely many. Okay. Look at the corresponding eigenvalue problem. If lambda is 0, then this problem has no solution or infinitely many. The operator here is the matrix. Okay, now look what we did today. Our operator is the operator which is a differential operator. It's acting on u and it's not acting on a x, a vector x, but it's acting on a function ux. But I'm solving the same problem, Lu is f. The nearby eigenvalue problem is L phi is minus lambda phi. See here the same eigenvalue problem. So that's similar. If lambda is 0, we saw that the problem was only solvable if an inner product was equal to 0. And if that inner product was not equal to 0, then we had no solution. In the first case we had infinitely many solutions or no solution. If all the lambdas are non-zero, we have a unique solution. If all the lambda are non-zero, we have a unique solution here as well. And now you see the structure. Whether we have here a matrix as an operator or a differential operator, it doesn't matter. This remains the same. You can draw the same conclusions from this to this. This is what we did for ODEs so far. Well, for PDEs we're going to do the same thing. But then this operator will be a partial differential operator. Yeah, and then you can try to repeat all those things as before. This is the mathematical structure that we try to show you as well. Yeah, so if you're still a bachelor student in the first or second year, then most part this is what you're doing. The further you come, you're going to do this. And this can be simple differential operators, or partial differential operators, or integral operators, or whatever operators. Yeah? But this structure is coming back over and over again. And that is what I meant with, if you see the structure in mathematics, then life becomes much, much easier. But it takes time to study that and to see that. And the further you come, the more you see and the more easy it becomes. Yeah, and that's also what we try to tell you in the course of PDEs. Then if we are solving PDEs, we are also doing it in more or less the same way. Only the dimensions are higher and, well, it changes a little bit in the details, but the structure remains the same. Try to see that. Yeah? And this structure is very important to see. Yeah? That group, I told it, but here T was also discussing the same thing. Yeah? And as soon as you see here this structure, yeah, then this or this becomes very easy. Yeah, clear for everyone?
Yeah.
We will see you tomorrow morning. Yeah? See you.